Last section we introduced the definite integral as a way to write areas under curves, and we saw how we could use indefinite integrals and antiderivatives to compute those definite integrals. Today we're not really going to introduce anything new, but we're going to look at ways to manipulate the definite integral to find various areas. Specifically, what would happen if we have two curves? Some y equals f of x and y equals g of x. Let's draw a picture of what's going on here. We have one curve here. So let's even do this in another color. We have a curve up here. This is f of x. And another curve here. This is g of x. But we also have limits on here, a and b. And we draw vertical lines connecting our curves at a and b. And we're trying to find this area between those curves. Instead of just trying to find the area under the curves down to the x-axis, we want the area between them. Well, how would we do that? Well, we could just continue on from the topmost curve, so in this case the f function, and continue all the way down to the x-axis and find the area under that. We know how to find that area. That's just the integral from a to b of f. But then we want to get rid of this extra area underneath. If we can take this area out of it, then all we're left with is the top part. So we'll take all this area out, but we know how to find that area as well. That's just the integral from a to b of g. And if we subtract that out, then we'll be good. The area between the curves will just be that difference. But here we can even do a little bit better. Because we're able to break apart integrals over a sum or difference, we can also put together a difference of two integrals, as long as the limits are the same. This is really the integral from a to b of the difference between f of x and g of x. And being able to put them together like that is very useful when the functions might have like terms that can cancel. And so we don't have to worry about integrating those like terms, or maybe we can just save ourselves on combining some like terms. But the main thing to note here is that we can find the area between these two curves by taking this difference and integrating it, but we just do have to remember which one's the top function, which one's the bottom function. If we swap these, we wouldn't be working with an area anymore. We would actually be working with the negative of the area. Let's go ahead and look at a problem. Let's look at problem 3. They're wanting us to find the area contained between two curves. We have f of x is x squared minus 4x plus 3, and g of x is negative x squared plus 2x plus 3. Now the book does have a drawing of this in the book because it is very useful to actually graph the functions first. Because we need to know which function is the top function, what's the bottom function. In this particular case, there's also the question of what are the limits of integration. They didn't give us those. So let's see what the situation actually is. We have our first function. We have x squared minus 4x plus 3. So we get this nice parabola here. But then we have another parabola coming from negative x squared plus 2x plus 3. And here we can kind of see why they didn't give us limits. When we're trying to find the area between them, this is a pretty common situation where the curves actually do intersect at different points. We can actually just go ahead and try to find these intersection points and find the area contained within both of these two graphs. We've got this region in here. Now, to find those limits of integration, we technically need to set our two curves equal to each other and solve. Might be able to guess what the points are actually going to be. Of course, we can see that it looks like they intersect at 0, 3 and at 3, 0. Basically, x equals 0 and 3 should be correct. But let's go ahead and solve anyways. So we want to know when these two curves give us the same y value. Go ahead and move everything to one side. So I'll bring an extra x squared over here. We have to subtract 2x from over here, so that makes a 6x. And of course, the 3's actually completely cancel each other out. We can go ahead and factor out a 2x from this. And as we suspected, when x is 0 or when x is 3, we get 0. So that means our area is going to be the integral from 0 to 3 of the difference of these two curves. Now, remember, we do need to know which one's on top. The top curve here is actually g. It's a negative x squared plus 2x plus 3. And that's kind of important. Otherwise, if you put them in the wrong order, you're going to get a negative. Really, it's not too big of a problem to correct because you'll still get the same correct value, but the negative of it. So you could just change the sign at the end. But it's nice to be able to make sure we do it correctly the first time. And it's going to be important when we run into some certain situations in our next problem. So go ahead and put g first. And then I'm going to subtract what I have for f. Putting them in parentheses for the moment just so I can make sure I distribute the negative here correctly. So we have a negative x squared. Here we also have a negative x squared, so that becomes a negative 2x squared. We have a 2x, but then we have a negative of a negative 4x, so a plus 4x. So we get a plus 6x. Then we have a 3 minus a 3. So those cancel out. And you might notice here that what we got is pretty similar to what we got when we were actually trying to solve. When you have to find points of intersection, you end up seeing a similar thing in your integrand. Though we actually got the negative of it, so we can't really count on doing it correctly unless we know what we're doing. We need to find an antiderivative of this. So x squared, we raise the power by 1, so we have an x cubed. We divide by the new power, so we divide the negative 2 by 3. Here we have 6x. The x becomes an x squared. We divide the 6 by 2, so we just have a 3. And we evaluate that from 0 to 3. And now we just need to put in our limits. We put in our top limit first. We plug it into this function. So we have negative 2/3 times 3 cubed is 27. Plus 3 times 3 squared is 9. When we plug in 0, well, both those terms become 0, so that's actually all that's just 0. I don't do anything more than that. And then you could use a calculator, or this actually isn't too hard to figure out, because 27 divided by 3 is just 9. But we just get, in total, a 9. That is the area between these two curves. And if you want, you can actually check in GeoGebra. So remember, we had this command of integral where we could put in a function and it's the a and the b, and it would give us the integral underneath that curve. Well, it also has an integral between that allows you to put in two curves. So f. Okay, I was trying to select f, but okay, I'll just type it in. The integral between f and g, and you'll have to actually give it the limits. So we have from 0 to 3, and it'll even draw a nice picture there. It'll shade in the region that we're actually working with. And oh, yeah, notice I put in f first. Technically, g was the top function, so I should have put them in the other order. They gave us negative 9. If I put them in the correct order, we get the positive 9. Let's move on to problem 7. Here, again, we're just given two curves. F of x is 3 times x cubed minus x. And g of x, well, g of x is just 0. Basically, one of our functions, one of our curves is just the x-axis anyways. So this is kind of what we were doing on in the previous section, but there's going to be a little bit of a twist here. So we should just go ahead and start off with graphing it. In fact, all the problems that we're going to do today, we'll start off with a graph. Wait, that's supposed to be cubed. So 3 times x cubed minus x, and we have this particular curve here. We could go ahead and write in g of x as 0 if we want to. It'll give us a nice color for that, I guess. But notice here that our cubic actually intersects the x-axis multiple times. And so the area that they're looking for is any area that is completely bounded by these two curves. That would be this region here and this region here. And we're asked specifically to find an area. If we were just to integrate our cubic from -1 to 1, you can kind of tell that those are where the intersection points are, this region over here would just be a negative value, a negative area. In fact, these would actually, because of the symmetry of the problem, these would actually cancel each other out. The integral from -1 to 1 would actually be 0. What they want is us to actually find the total area of these two regions. So they want this region to become a positive area. So what are we going to do? Well, we're going to treat this as two separate regions with different tops and bottom functions. So in this region here, we have a top function of the cubic and a bottom function of the x-axis. In this case, the top function is actually the x-axis, and the bottom function is the cubic. Of course, we do need to know what the intersection points are. But I think it's pretty clear that those intersection points are 0 and plus or minus 1. Technically here, you'd have to set this equal to 0, factor it, and all that. But the factors here are x, x minus 1, and x plus 1. Exactly what we expect to get. So we're going to have to do this as two separate regions. That means two separate integrals. The first integral is from -1 to 0. In that case, our top function was our cubic. So 3 times x cubed minus x minus 0, but I don't really need to write that one. Then we add the integral from 0 to 1. This time 0 is our first function, our top function, and we're subtracting that. Now you don't actually have to write the 0 there if you don't want to. That doesn't really help us too much. But the point here is that we have to introduce a negative here to compensate for the negative area that we would have gotten from just integrating the original function from 0 to 1. We'll go ahead and take an antiderivative. So I'll move the 3 outside. It's not too important to have inside, but the x cubed becomes x to the 4th, and we have to divide by the 4. The x becomes an x squared, and we have to divide by the 2. Take that from -1 to 0. Here, let's pull the -3 out. So minus 3 times, well, we're still finding an antiderivative of x cubed minus x. And we've already found that antiderivative. We'll just reuse it here. That's from 0 to 1. So now, first we plug in our top limit, our 0. Of course, that just gives us a 0, so it doesn't really do much there. Then we subtract what we get when we plug in -1. So minus the 3 times, when we plug in -1, well, this actually is a 1, and this is a 1. The even power gets rid of that, so we have a 1/4 minus 1/2. Over here, we have minus 3 times what we get when we plug in 1. Of course, that's again going to be 1/4 minus 1/2. And then technically we have the negative 3 times a negative, so plus something, but when we plug in 0, we just get 0 anyways. So the zeros don't really matter. The rest of this, well, 1/4 minus 1/2 is a negative 1/4. The negatives cancels with this negative, so we actually have a 3/4. We actually get exactly the same thing over there. We get a plus 3/4 from that. And when we add those together, we get 3/2. And so these two regions, if we try to find the integral of both of them, so say the integral of f from -1 to 0, it writes it as 0.75. That's the 3/4 that we saw. And then this region over here would have the same. Yep, okay. So we have 2 copies of 3/4, and the total area is 3/2. Next, let's do problem 16. In problem 16, they're asking us to find the area between the curves negative x cubed plus 3 and y equals x. But they also give us 2 other curves. Well, they're limits. We're going from x equals -1 to x equals 1. And again, let's go ahead and graph this, just so we make sure that we know what we're dealing with. So we have negative x cubed plus 3, and we have y equals x. Go ahead and put in the limits. GeoGebra will allow us to graph those vertical lines. And so we have a region here that is completely bounded by all those curves. And we notice here that the top function is our f, our negative x cubed plus 3. Our bottom function is y equals x. And we don't really have to find any limits of integration. We don't have to deal with this point of intersection at all. So this is actually a pretty simple one to write down. So it's going to be the integral from -1 to 1. We put in our top function, subtract our bottom function, and we're good to go. We just proceed from here. Though it was useful to graph it because we needed to make sure that we knew which one was on top and which one was on bottom. We also need to make sure that they didn't intersect somewhere. If they did intersect, well, we'd have to do some, probably split up our integral like we did in the last problem. There's no like terms here, so nothing really cancels. We'll just go ahead and find an antiderivative right away. So we have negative x cubed. The x cubed, we raise the power to a 4, and then we have to divide by the new power. A 3 just becomes a 3x. And then the x, or the negative x, becomes an x squared, but then we have to divide by the 2 as well. Go ahead and plug in 1. That just basically gets rid of all the x's. We have the negative 1/4, we have a 3, and we have a negative 1/2. Next we plug in -1. Well, the -1 is just going to be a 1 in the case of the x to the 4th and the x squared, but it's going to change the sign for the 3x. So we're still going to have a -1/4. The 3 is going to become a -3, and we're still going to have a -1/2. And in fact, that's kind of interesting because the -1/4 minus a -1/4 cancels out, and the -1/2 and the minus a -1/2 also cancels out. So we actually have a 3 minus a -3, so 3 plus 3 is 6. Which we could actually find that here as well. And it gives us the area is 6. Really nice. Moving on, let's do problem 25. Again, they give us 2 curves. We're looking for the area between x times e to the negative x squared. And then we just have a bunch of lines. We have y equals -1, we have x equals 0, and we have x equals 1. Again, let's just go ahead and graph this thing. Give us a good idea of what's going on. We have y equals x times e to the negative x squared. We have y equals -1, we have x equals 0, and we have x equals 1. So we end up with this region here. They want us to find this region inside here. Oops. Again, we're graphing it specifically because we want to know what the top function is. We want to know what the bottom function is. We want to know that they don't intersect anywhere, so we don't have to split up our integral. But this is pretty standard. But top function is definitely our exponential thing. The bottom function is actually a line. It's just a constant. But we still have to include it. And our limits are just what our limits are. So very easy integral to set up. The integral from 0 to 1. We have x e to the negative x squared, because that's our top function, minus our bottom function of -1. So minus -1 just means we add 1 to it. So nice and easy. Well, at least the setting up was easy. Evaluating the integral is going to be a little bit more interesting, because we're going to have to make a substitution for this first part in order to make this work. The obvious substitution to make here is actually just put the negative x squared from our exponent as u. Then du is just going to be -2x times dx. Of course, we have the x, but we don't have the -2, so we're going to go ahead and divide that. Now, we do need to be careful here, though, because we do have an x, but it's only on this first term. The second term can't really be part of the substitution, or we're going to have to do some extra tricks to deal with that. It's actually a lot easier just to kind of deal with these as two separate integrals. One integral where we have the exponential part, and another integral where we just deal with 1. This integral is really easy to just do by itself. This integral is where we do use the substitution. So we'll have the integral of e to the u. The x dx is a -1/2 du. So we end up with a -1/2 in front. Of course, we do need to deal with our limits. When we plug 0 and 1 into -x squared, well, 0 is just going to give us a 0. 1 is going to give us, well, it was 1, but now it's a -1. Notice here that our limits are actually, you might think they're in the wrong order. But that doesn't really matter to us. We could actually swap the order if we want to. I'm going to deal with this integral first before we move on, though. Notice here, 1 just becomes an x. We'll take that from 0 to 1. In our next step, let's go ahead and put these in the order that we expect them to be in. We'll swap the 0 and the -1, and that changes the sign that we have out in front. We actually change the negative to a positive. This one here, when we plug in 1, we get 1. When we plug in 0, we get 0. So we'll have 1 minus 0. And just getting a plus 1 from that. And now we take the antiderivative for e to the u. That's just going to be another e to the u. We're going to evaluate that from -1 to 0. We still have a plus 1 on the end. When we plug in 0, well, e to the 0th power is 1. So we'll have the 1/2 times 1 minus when we plug in -1. Well, e to the -1 is actually 1 over e. And I think it looks a little simpler if we actually go ahead and combine the 1/2 from this first one. If we distribute the 1/2 to the 1 and the negative and the minus 1 over e. But 1/2 and 1 gives us a 3/2. So 3/2 minus 1 over 2e. It's probably the nicest way of writing that one. So we can say that that is the area between these two curves, and inside of this region. Let's go ahead and do one last problem. Let's work on problem 29. Here again, they give us various curves. We have a y equals 8 over x. We have a y equals x squared. We have a y equals 0. We have an x equals 1. And an x equals 4. There's a lot of stuff that they're giving us here. Why are we given all this stuff? Well, 3 of them are lines. Those are pretty simple things. Then we have a quadratic and a 8 over x, whatever that curve actually is. So go ahead and plot all this stuff. And maybe we'll see why they gave us everything that they gave us. So we go ahead and plot our two curves. They don't really seem to have, I mean, they intersect somewhere, but still doesn't really give you any indication of what they're really looking for. They give us y equals 0. The x-axis is going to play a role. They give us x equals 1 and x equals 4. We have these two boundaries. So what they're really looking for is this region right here. But notice that the two curves aren't really the top and bottom of the region. The bottom of the region is just y equals 0. It's the x-axis. The top is actually consists of two different parts, using one of the curves as one of the top parts, and the other curve is the other top part. It would actually make more sense here to kind of treat this as two different regions. One where we use the x squared as our top part, and one where we use 8 over x as the top part. That does require that we find this intersection point here. You could go ahead and set them equal to each other, but I'm just going to tell you right now that they intersect when x equals 2. When x equals 2, we have 8 over 2 is 4, and we have 2 squared is 4. So that point there is 2, 4. So really we have two different areas, and we're going to add them together, find them using integrals and add the results together to find this area. So we're not really, don't just blindly go ahead and subtract your two functions and go from there. You actually do want to figure out exactly what is going on in your region, because sometimes they can throw you curveballs like this. So from 1 to 2, that's this first region. We're going from x equals 1 to x equals 2. Our top curve here is just our x squared. The bottom is the x-axis, so really we're just integrating x squared. But then we have from 2 to 4, this time our top curve is the 8 over x. And we just do our integrals. They really don't even interact with each other. When we integrate x squared, we raise the power to a 3, and we divide by the new power, taking that from 1 to 2. When we integrate 8 over x, well, the 8's really just kind of tagging along, so we'll ignore that for the moment. We have a 1 over x, and remember, the antiderivative of 1 over x is the natural logarithm of x. You could leave off the absolute value here since we're only dealing with positive numbers. I'm going to go ahead and write them still. Go ahead and plug in our limits. Remember, plug in the top limit first. When we plug in 2 here, 2 cubed is 8, so we end up with an 8/3. Then we plug in 1, we just get a 1/3 that we subtract. Over here, we plug in 4. Not really any simplifications there. We just, other than we don't need the absolute values, so we get 8 times the natural logarithm of 4 minus 8 times the natural logarithm of 2. And you could say that's our answer, but we could go ahead and simplify things. 8/3 minus 1/3 is a 7/3. Here, a difference of two logarithms is actually a logarithm of a quotient. We could go ahead and take this as 8 times the natural logarithm of 4 over 2. which we can simplify that just down to the natural logarithm of 2. So, an easier way of writing that one down. And really, we can actually see exactly what's going on here. The first region actually has an area of 7/3. The second region has an area of 8 times the natural logarithm of 2. So the integral of the x squared is g from 2 to 4. And wait, sorry, that's from 1 to 2. So 7/3 is 2.33. The integral of our f is that's our 8 over x from 2 to 4, and that's this one here, which I guess is around 5.55. But the total here is just adding them together. So again, we didn't really introduce anything brand new. We're still just working with definite integrals. We're still finding them by doing the antiderivatives, all that kind of stuff. But as long as we actually can interpret what our graphs look like, we can use those to find areas pretty easily. All right. In the next section, we will get into some integrals that maybe we can't actually do easily, but we'll find a way to approximate those. So I'll see you guys in that next video.